similarity measures, which is given two strings x and y, how similar are they? Ideally, we want a similarity measure that is both robust, meaning small changes in the inputs give only small changes to the measure, and fast to compute. It has application in bioinformatics and information retrieval. And the most well-known of them is the edit distance, which is find the smallest number of insertion, deletion, and substitution required to convert one string into the other one. And the edit distance of katakat to atakat is just you can remove the G and remove the A in the middle of atakat, and the edit distance is only 2. It can be computed in quadratic time using a very classic dynamic programming, and this is probably optimal because Backers and Indyk showed in 2015 that the edit distance can't be computed in strongly subquadratic time unless CES is false. CES is the strongly exponential time hypothesis that is generally believed to be true and will come up very often in the lower bound results in this talk. However, there have been recent results in approximating the edit distance. One in 2018 by Chakraborty, which gave an n to the power 2 minus 2/7 time and an approximation factor that was above 3 plus epsilon. And in a paper in Stock 2020, there is now n to the power 1.6 time and an approximation factor of 3 plus epsilon by Goldenberg et al. And Antony and Nostatsky showed this year that there is an n to the power 1 plus epsilon time approximation, but the approximation factor is doubly exponential in 1 over epsilon. So another way you can go, starting from the fact that the edit distance can be computed in strongly subquadratic time, is looking at other similarity measure. And one of them is the longest common substring that we already mentioned in the previous talk, where we want the maximum length of a string that occurs in both strings. So LCS of the AAGC and AAGAC is just 3. And it can be computed in linear time, for example, via the suffix 3. And the problem is it's not robust. It can change a lot when we just change a few characters in the input. So this works focuses on the longest common substring with k mismatches, where you give yourself an integer k and strings x and y of length n, and you want to find the maximum length of a substring x that occurs in y with at most k mismatches. So if we take again the example we had before, we are allowed 1 more mismatches, so we can match 1 more character for k equal 1, and we have an LCSK that is 4. It's also closely related to the K-max, the K-mismatch average common substring distance that was introduced by Lamster and Morgerson in 2014. So first, some results on the longest common substring with K-mismatches, exact solution. All solutions have linear space. And the 2 first solutions are by Floor et al. In 2015. The first one is for k equals 1. And you can have a solution in n log n time. For all of the k, you also have a solution in n squared time via dynamic programming. And all the other results improve on this one. But for a k that is equal to roughly log n, you still have a quadratic solution. And this makes sense as Koshmaker et al. Showed in 2019 that in general, LCSK cannot be solved in strongly subquadratic time unless CES is false. CES is still the strong exponential time hypothesis. And from there, they introduced another problem that was the longest common substring with approximately k mismatches, where in addition to the integer k, you give yourself a constant epsilon strictly positive, and you want the length of LCS approx k to be larger than LCS k and to be the length of a substring of x that occurs in y with less than 1 plus epsilon k mismatches. So if you give yourself an example, k equals 2 and epsilon equals 0.5, then in LCSK you're allowed 2 mismatches and in LCS approx k between 2 and 3. And this way you can have a LCS approximate that is of 6 with a witness that is the following opposed to just the LCSK. It's more robust than LCS and it's easier to compute. And after introducing the problem of LCS approx K, Koshmiga et al. Showed the first results that was n to the power 1 plus 1 over 1 plus epsilon log square time, and n to the power 1 plus 1 over 1 plus epsilon space for any epsilons between 0 and 2. The main idea was locality-sensitive hashing, but it used a very complex system of hash function, and the space is super linear, which is not good compared to the results on LCSK that all had linear space. So we give 2 improvements. One that improved both in time and space, but still has superlinear space. The time is n to the power 1 plus 1 over 1 plus 2 epsilon plus O of 1. And both results are for all epsilon strictly positive. And the second result in time compared to the previous one, it just has an additional log n factor, but the space is linear. The main idea is still locality-sensitive hashing, but the system of hash function is much simpler, and the linear space makes it overall more practical. In this talk, my goal is to give the main idea for both time improvement and linear space. But to do this, I will first have to show how we go from LCS approximate to a decision variant of the problem, because we use it for both results. And we do that by using the 20 question game with a liar. In the 20 question game, you have 2 players, Paul and Carol. And Carol has in mind 2 numbers. And the goal of Paul is returning some number between A and B. And he has question of the form, is X strictly inferior to A? And Carol must answer yes if X below A, no if it's strictly larger than B. And she can answer anything if that's between A and B. And in the version where you play with a liar, Carol is allowed to lie a fraction of the time, and that fraction must be below R. We used in our paper a corollary of Dagstad, Gax, and Winsler in '92 that says that for any R below 1/3, Paul can win by asking roughly log n questions. And then we can use this technique to actually solve only the decision variant of our problem, which is the following. In addition to the integer k and the constant epsilon, we give ourselves an integer L, and our goal is to answer yes if we're below LCSK of x and y, and yes or no if we're between LCSK and LCS 1 plus epsilon k, and no if we're above LCS 1 plus epsilon k. And the answer must be correct with probably at least 3/4, so we can apply the results on the 20 question game with a liar. And then, yes, we apply it, we solve once we have a solution for the decision variant, we solve the longest common substring with approximately k mismatches by just putting A to be the LCSK, B to be the LCS 1 plus epsilon k, and our algorithm plays the role of Carol, which might lie sometimes, as we only are correct with a certain probability. So now I'll present the the main idea of how we get the time improvement result, and this is via another problem, which is the approximate near neighbor, where you give yourself C that is above 1, R that is strictly positive, and a failure probability F, a set of point P in D dimension. And you must create a data structure that answers for any point Q in the dimension. If there exists P that is relatively close to Q, meaning at distance less than R, then you must return some points that is at distance CR of Q, with probability at least 1 minus F. And we are going to use the results from Andoni and Rasenstein in 2015. that showed that the approximate near neighbor can be solved with a data structure requiring O to the power n to the power 1 plus rho plus O of 1 plus dn size, and a query time that is also in n to the power rho plus O of 1, and where rho is just 1 over 2c squared minus 1. And the main idea of how we applied this result to our problem was first that we used the dimension reduction on all L-length substring of x and y. Because remember, we're trying to solve the decision variant that tells us whether L is between LCSK and LCS 1 plus epsilon k. And so we can focus on those L-length substrings. For the dimension reduction, we used a corollary of the Johnson-Linders-Strauss lemma. And it doesn't, the main thing is that it doesn't change the Hamming distance too much between the reduced points and the original substreams. We have a link between the length of the distance between the reduced points and the Hamming distance of the two L-length substrings. This way, we can build the approximate near neighbor structure for all reduced substring of x, and then query the structure for all reduced substring of y. And if we find 2 points, so the reduced points, so that are close enough between that are distance less than CR, we know by our dimension reduction that it means that Hamming distance is at less than 1 plus epsilon k. We check, and then we can return yes. This solves the LCS with approximately k mismatches in n to the power 1 plus 1 over 1 plus 2 epsilon plus O of 1, which is an improvement. But the problem is both that it's not yet implemented. It uses nonlinear space, even though it improves on the previous result. And the paper from Andoni and Rosenschein uses non-trivial techniques, which might make it a bit harder to apply. So I'll now give the idea on how to have a linear space solution. And this is based on locality-sensitive hashing, which I've mentioned several times already, but haven't defined. And we say that the family of f of hash function is called locality-sensitive if for all S1 and S2 strings of length L, and a hash function h belonging to f chosen uniformly at random. If the Hamming distance between S1 and S2 is less than k, then the probability they're equal, the hashes are equal, is larger than P1. And on the other hand, if the Hamming distance is larger than 1 plus epsilon k, the probability the hashes are equal is less than P2. This can seem a bit particular as a definition, but the set of hash function we use is quite simple. It's a set of projection onto a single position, meaning Pi projects on position I. It's always for a string of length L. And so P2 of cat is just the second letter, which is A. And by choosing one position among L uniformly at random, it's quite easy to see that if there are less than k mismatches, then the probability they are equal is the probability we don't take any of those less than k mismatches. And this is 1 minus k over L. And on the opposite, if they have more than 1 plus epsilon k mismatches, then the probability that S1 equals HS2 is the probability that we don't take any of those more numerous mismatches, which is 1 minus k 1 plus epsilon over L. And starting from there, there are several tricks to actually make this work. First, we don't project on only one position. We project on M position to have more idea of how many mismatches between the strings are there. And we don't take only one hash function. We take a set of hash function to have more chances to see the strings and to see what are collision. So we take this set of hash function and apply them all to the all L-length substrings of X and Y. And we explore the pairs of L-length substring that collide, meaning all triple S1, S2, and H, so that HS1 equals HS2. But it might be too slow to compare naively HS1 and HS2, so we actually use the carving fingerprints of those hashes to know if they're equal. And on those collisions, we then look at sketches obtained by dimension reduction to test the distance between the substring. And the bottom line is that if there is a pair of L-length substring of X and Y with less than K1 plus epsilon mismatches, we will find it with a constant probability, and we can always repeat the experiment to then apply the 20 question again. We really wanted to implement some of our algorithms to have an idea of how practical they are. But none of the previous solution had been implemented. In particular, none of the LCS approx solution had been implemented. So the algorithm that seemed to be practical enough was the dynamic programming one by Flory et al. And we compared our algorithm with the dynamic programming one, both on random string and on string extracted from E. coli of lengths ranging from 5,000 to 60,000, and K equals 10, 25, and 50. The first thing we compared the two implementation on were the running time, and this running time was obtained by, for each length, performing 10 independent experiments to have an idea of the standard deviation. And we can see that so the orange one is the dynamic programming one, and for all epsilon larger than 1, the linear space algorithm is indeed more efficient. However, there is a big standard deviation for epsilon equals 1, which is probably due to how we implemented the algorithm. And but however, it's negligible for epsilon equals 1.5 and epsilon equals 2. And the good news is for strings of length 60,000, we actually have a gain of factor up to 10. However, as Flory gives an exact solution and we give an approximate solution, we can not only compare the runtime, there's also the distortion and accuracy. And we can start by noticing that we can only err by returning a string shorter than LCSK. We cannot have a string that has more than K1 plus epsilon mismatches. Therefore, we estimate the distortion by two values, Rmin and Rmax, which are the minimum of the ratio between LCS approx K and LCS K. And the error is when we actually have a string that is lower than LCS K. And the main thing we can notice is that by augmenting epsilon, you diminish your error rates, but Rmin and Rmax grow. The conclusion is that the implementation and the linear space algorithm is quite simple and practical. It is faster than the dynamic programming solution for epsilon strictly larger than 1. It has a small distortion compared to LCSK, even though there are no theoretical guarantee. And it has quite a good accuracy. And to say it one more time, we bring two new approximation algorithms that solve the problem in one in n to the power 1 plus 1 over 1 plus 2 epsilon plus O of 1, and one with just a log n additional factor and linear space. And one final result I had never mentioned before in this talk, but that we give in the paper, is that we show the first lower bound on the longest common substring with approximately K mismatches, and it is that it cannot be solved for all epsilon in strongly subquadratic time unless SAS is false, which is coherent with our results, as we always have epsilon as a parameter of the time complexity. Thank you for your listening.